In the previous lecture, we have learned how to derive characteristic function of a model which belongs to a affine jump diffusion class. In this lecture, I will show you how to use this characteristic function to either recover corresponding density or perform efficient pricing. Let's take a look at the content of today's lecture. First, I will start with a definition and a little bit of history of Fourier transformation. Then I will show you how to perform implementation in Python. We will look at different quality results depending on the settings of the fast Fourier transformation. Then we will move to the cost method and density recovery. I will make comparison of the Fourier transformation method of FFT and the cost method. Again, I will show you how to perform implementation so that implementation is also efficient. And finally, we move to pricing of European type options using characteristic function and the cost method. Finally, we will wrap it up with some experiments and implementation details. I will also show you how to do the implementation very fast, such that you can perform pricing for multiple strikes at the same time. So far, we have learned that once we have derived a system of differential equations, stochastic differential equations for pricing, it is very difficult to calculate density for such a model. Computation of density, essentially, it is very limited to very simple, typically 1D models. However, if we know that our model corresponds or belongs to the class of affine diffusion models, we are able to find the corresponding characteristic function. Once we have the characteristic function, the next step is to apply numerical technique to compute corresponding density. This is the subject of this block. The technique that we are going to use to compute, to invert, to map a characteristic function to density, it is based on Fourier transformation. So the standard definition that we start with is a density at given point x is equal to 1 over 2 pi. We have integral over the real domain, and then we have an exponent of minus iux, characteristic function of u. So as you can see, if you like to have a density at given point x, we need to compute this integral. So this means it's a very computation you can think of expensive, because if you need many x's, then we need too many of those integrals. So let's take a look at the pricing formula when actually will we need this so many x's or not. So the pricing equation that we always look at is the value of a derivative at the maturity discounted with the money savings account. If we consider money savings account with a constant interest rate, then essentially this integral will be equal to this expectation will be equal to the integral over the real part, real axis. We have e minus rt. And now we have a payoff at time t. So this could be, for example, this payoff could be maximum of st. Well, actually, in our case, let's consider x. That's for simplicity. So we have x minus k0 times the density of x. We have here x dx. So as you can see, if you like to calculate this integral, we need to discretize this integral, and then for every x in our domain, we need to compute first this density. To get this density, essentially we need to compute this integral. So in essence, if we have this direction, in a u direction and x direction, we have endpoints. Essentially, we can think of O n squared operations, and that's typically it's considered to be very expensive. In this block, we will learn not only how to do it in an efficient way, but I will show you how to apply fast Fourier transformation, so the improvement of this representation, in order to get to a much faster representation when we have n log n operations. So it's much more linear in terms of operations. Okay, the first step is to move away from this representation and reduce the domain for you by using the inversion lemma. Inversion lemma states that if we would like to recover density f from x, we have to do the following. Then we have this following expression. We have 1 over pi, a real part, of the integral of 0 to infinity e minus ux, characteristic function of u du. If we compare these two expressions, we see that we have, of course, the real part that we need to take. That's a very cheap operation. On the other hand, we have our integral has reduced domain. So instead of going minus infinity to infinity, we have 0 to infinity, but we also need to have it factor 2. As you can see, it's a half here. It was basically this expression, this multiplied by 2, we have the relation. So this is first step in our derivation for fast way of calculating density for using the fast Fourier transformation. So let us start with the definition of the characteristic function. We have 1 over 2 pi, and then we have the integral we already have seen. First step would be to divide the domain into two, from minus infinity to 0, and from 0 to plus infinity. As you can see, term under the integral, the terms under integral are exactly the same. We take this integral here, we do the following. Because we have integral from minus infinity to 0, we do a change of variables. So we define new variable which is equal to minus u. Then we have the following. Then this integral becomes 0 to infinity, and then we have a e minus, then we have I vx, characteristic function at minus v dv. Now we have to note the following. By taking the conjugate, so this conjugate is the operation once we talk about the complex numbers of the first integral, and using the fact that the conjugate of an exponent equals to exponent of conjugate, we find the following. So we take this expression, here. We see that integral is essentially a summation, so conjugate of a sum and sum of a conjugate, so integral, and then we see that conjugate essentially would only change the minus sign in front of the first exponent, and then we have phi, the characteristic function of u, because characteristic function, we know the characteristic function is defined as the expectation of e I u, and then we have x, right? So we know that this summation expectation is just integral, so it's a summation. So we only would change the I in front if we do the conjugation, and then because some integral is summation, the conjugation would go outside of this integral. So this is the first step what we do. The second step is to put things together, and then we have the following. So this is just a repetition of what we have seen before, and now we have half, so 1 over 2 pi, and then we have exactly the same integrals. However, the right-hand side integral is a conjugate. And now we use the property from the complex numbers, which states that if we have a z, which is a complex number, and we take a conjugate of z, then it is equal to 2 times the real part of z. Therefore, so we see this is a complex number, this is a complex number. This means, and also we take a conjugate of this. This means that this expression is equal to 2 times r of the integral. And this is what was necessary to derive to prove this lemma. Next step in our derivation is the construction of the grid. So obviously we are interested in computation of the characteristic function, not only in a space of U, but we also would like to get the density for every x. So essentially we are thinking of a grid. So let us take a look here. We have a grid. So this would be our x, which we will have here x min, x max. X min and x max, you can think of boundaries at which your density, it will become very, very close to 0. So this means that you have the decaying of the density goes to 0. So if you have a density, of course, if you consider normal distribution, for example, then of course the support, the domain for normal distribution is minus infinity to plus infinity. But of course, in practice, once we talk about implementation, we need to define certain domain. And this would be also the case here. So we choose some number for which the density is close to 0. And the same for the right-hand side. So we have a left and right tail of the distribution. We choose the x min and x max. The second dimension is u. So for u, we already know that once we talk about inversion theorem, we have 0 to infinity. So this means we start from a 0, and then we have also, we don't have infinity, of course, in computer language, so we have u maximum. And essentially what we have now, we have a grid, which will be something as follows. This means that if we have chosen x, for which we would like to calculate our density of x, then we need to calculate this integral, and this would give us this density of x. So because we would like to do these operations at once, this means that we would like to get density for multiple x's at the same time. For that reason, we define this grid. So this grid will be for a grid of u's, grid of x's, and then essentially we would like to recover the density values at all those grid points. As you can imagine, once we have computed the density at all these grid points, so we are able to recover this density at every grid point here. It doesn't necessarily mean that this is exactly the grid point that you are interested in. For that reason, we also will be using later some kind of interpolation, but this is rather a technical detail that I will present you in once we go to Python code. But okay, so now we define a number of grid points. So we have n grid points that will be used for our domain, for domain of u, and actually we use domain of x. So we assume that number of points in each dimension will be the same. So actually this is not really rectangular, it is a square domain. So now, since we have reduced our computation of domain from -infinity to +infinity to 0 to +infinity, we do a little bit of simplification here. We would just define a new integral from 0 to infinity of function gamma, and function gamma is equal to this expression here. Next step is to redefine or define the integration routine we would like to perform on this integral. So integral is here is the continuous. We would like to have a discretized form, and discretization would correspond to our grid that we would like to develop. Of course, first thing we have to choose is the upper limit of the integration. For that, we will choose u max. As you remember, when we were plotting characteristic function was spinning in a kind of tube. This is what you could think of. Then u max determines the last moment where the spinning goes to 0. This is our limit. Later, once we go into the coding, we will see exactly how this limit can be chosen. Maybe just as a refresher, I would like to show you how to perform trapezoidal integration for a given function. First of all, we define some u maximum. We have our function gamma, which could be as follows. So this is our function gamma of u. We have an equally spaced grid. So this is delta u. And the integration that we have chosen in the transformation, it is trapezoidal integration. This means that every point on the grid, we will just build small trapezoids. So it's, for example, here, 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 and so on. So this means that if you like to calculate integral, we essentially need to sum over all those trapezoids. So this means that integral from 0 to u maximum of our function gamma u du is equal to, and then we have, of course, first term will be gamma of u1 plus gamma of u2 over 2 times delta u plus gamma of u2 plus gamma of u3 to delta u plus, and of course, the last term will be gamma of un minus 1 plus gamma of un divided by 2, and then we have a delta u. If we collect, of course, all the terms, so we can take half and delta u outside, so we have a delta. Let me just correct here. We would have a delta u over 2, and here we have a gamma of u1 plus we have a 2 times gamma of u2, so it's a 2 times gamma of u2 plus 2 times gamma of u3 plus 2 times gamma of u n minus 1 plus single gamma u n. This means we have a delta u over 2. We have 2 times summation of gamma functions of u k from k equal to will be 2 to n minus 1. And then we have a plus gamma u1 plus gamma of u, as this is not 2, but gamma un. And finally, we can write this expression as a delta u times summation of k equal to 2 to n minus 1 gamma u k plus half. And then we have summation of these two elements. We have gamma u1 plus gamma of u. And this is actually what we can see also in this representation. So we have a delta u over 2, and then we have a first term, we also have a last term, and we have a 2 times all the terms that we have seen already in between, right? So we have integral the summation from n equal to 2 n minus 1 gamma n u. Okay, we can of course get rid of it of 2. We can just put it inside the bracket. Then we have delta u, and then we have a summation from n equal 2 to n minus 1 to all these midterms we can think. Plus we have for the first and the last term half of them. Now what we have to choose, we have to choose some configuration regarding the grid that we would like to build. First, we choose some n. This will be number of grid points. And Umax will correspond to number of grid points times delta U. So once we choose maximum Umax, we can, and then number of points that we like to have in our transformation, then that will define our delta U. So Umax is essentially a parameter, n is also a parameter. So once you specify those two parameters, you have immediately defined what is your delta U. Then every point on the grid will be defined as follows. This will be nth point will be n minus 1 delta u. So if we have n equal to 1, we see it's a 0. So that corresponds to the lower bound. And once we have the last point, so be n, then we have n minus 1 delta u. And that will correspond to our u max. If we properly substitute, then we end up with our final point on the grid. For x, we have a minus b, this is also a free parameter, plus delta x times k minus 1. So this is, you see, we have a few free parameters that we have to tune. This b here, it corresponds to our, if we go back, this would correspond to our x minimum that we would like to define our grid. So once we specify starting point of our grid and also delta x, so the spacing, then we can define also the other direction of the grid. So you see that we have few parameters that we have to choose. We have to choose u maximum, number of points, and then we also have to specify our point b. The relation between delta x and delta u, it will be imposed by the Fourier transformation. So this is something that we should not worry about. However, those three parameters you can choose. Like I said again, like I said before, this configuration about particular set of parameters that need to be chosen, we will go through this once we will be looking into Python coding. Okay, so next step is that once we defined this integrals, the summations, we can substitute and use our new defined grid. As you remember, instead of function gamma, we had exponent, or actually instead of exponent minus ux phi, we had gamma, but now it's actually more convenient to go back. So gamma was convenient once we talk about integration, how to define the trapezoid integration. Now, once this is done, it's good to go back. So after substituting, so we have a u that we have to define our un. This is our grid, right, at every point. We have also xk. This is our grid for x. So this, after substitution, we end up with the following. So for every x, essentially, so this is still a function of x, we have integral from 0 to u max, gamma u du, and then we have our trapezoid integration where we perform the substitutions. So for u, we will plug in our un grid, and for our x, we specify our x grid, as you can see here. So this is dependence on x, this is dependence on u. We have a characteristic function evaluated at the un, And then we have those nodes, let's say boundaries of the trapezoid integration. In the second point, you can also notice one element that is maybe a little bit suspicious. And this is related that you can see here we have a minus. And however, before we had plus, right? So you may think that this is a typo, but this is actually not. It comes from the representation of the integral. So you can see that integral here right now, the summation comes from n equal 2 to n minus 1. But what we have done here, we define summation from n equal to 1 to n, which basically means that we have to subtract those terms. So this is something to keep in mind. Maybe it's not so much highlighted in the slides. It's easily not to notice that, but summation indices have changed. So please keep in mind. Then, of course, once we have those terms, we have to order them. And then we have this dependence on delta x and delta u. We have n minus 1, k minus 1, and then we have also this, let's say, three terms which depend also on n, and then on the maximum of the integration domain. Of course, at this point, you may wonder, what is the idea? Why we would choose? Why this looks a little bit messy? Why somebody would be interested in this representation? This will become a little bit clearer later. At this point, I can tell you that this representation, especially E, and then we have a minus and then some term involving pi, and then those two terms, so n minus 1, k minus 1, it fits nicely to the fast Fourier transformation representation. This means that once we have a function that you would like to integrate, and we are able to formulate this function in terms of, let's say, inputs for FFT, this is very beneficial for us because this means that we can just simply define our function, modify in a way that fits the inputs to the function for fast Fourier transformation, and we can just take full benefit of fast evaluation and fast implementation from the library. Typically, fast Fourier transformation, it is available in every library, so this is something that we are not going to implement ourselves. However, today I will also give you a little bit of details how this transformation is performed and why it is so fast. Okay, so next step would be to define a grid. So we have this relation. You can see we had the relation dx delta x delta u. For that reason, we will define some grid, which will be basically 2 pi over n. So like I said before, this is already you can see here, fast Fourier transformation requires this kind of function, which will be multiplied with these terms. Here you can see that this relation, it just gives us what is the relation, it tells us what is the relation between grid for x and grid of u. So it is nothing special. We can just freely set the grid sizes in the way that it fits the inputs for fast Fourier transformation. So after substitution, we end up with this following term. So we have this minus I 2 pi n, n minus 1, k minus 1. We have those three terms and the boundary terms. We also notice that this term here actually comes from except for b, relates to un. So this means we can also substitute. And this part times a function, it is fast Fourier transformation. This means that if we have a library which which allows us to compute fast Fourier transformation, typically is defined in this way. So we have a grid from n for u and x. This is also what we have. And then a function that is basically, it's here. It can be evaluated with fast Fourier transformation. Then we get our desired integrals for every x. And this is of course, very beneficial. So once we because we started with trapezoidal integration, we were able to represent it in a way that nicely fits to the algorithm for fast Fourier transformation. So this part, you can see this we do with FFT. Then we had to also add some correction terms. So the terms that corresponding to the initial and end point of the grid. And then we are ready to go to compute this transformation. Then we also have to keep, of course, of the all terms, they need to be multiplied with a delta u. Okay, then the summary, of course, and the implementation. Once we started from the inversion lemma, we have 1 over pi, the real part of this integral. This is what we have proven. And this can be calculated, or this is equivalent with the following representation. We have delta u over pi, so it comes here, real part. Then we have a fast Fourier transformation, which takes place here. So once we know characteristic function, we can just multiply with E I B U N. So this is just a grid that we would define for our Fourier transformation. We have a B, which is the minimum minimum x, pardon. And then we have two correction terms which come from also characteristic function evaluated at the beginning of your of the grid and at the end of the grid. One more thing to notice that you see that here we have x. However, this x here, it is not really present. X in here, it is essentially given in terms of grid. So like I already mentioned before, we have a grid for x's and u's. Now, of course, if you're interested in this particular x, which is between xi and xi plus 1, this is not really helping you. For that reason, we need to implement also some kind of interpolation, smooth interpolation between the corresponding points. In that way, because we have a discrete number of points, so for example, a few thousand points, if you like to have many, many points here, so millions of points, then it's recommended to use interpolation. Then you don't need to calculate so many, let's say, matrices that are necessary for the fast Fourier transformation. So far, we have derived Fourier transformation, but as you can see from this expression, at this point it is not really fast, because for every x that we have, we still have to build two-dimensional grids for every dimension of x and dimension of u. So at this point, this is not really beneficial. At this point, we can conclude that what we have derived here is the trapezoidal integration of the characteristic function. So essentially, once we want to have density, we still need to build a grid and sum all the terms in two dimensions if you would like to have it for multiple x's in order to get our density recovered for the whole domain. So at this point, it's still not beneficial. However, I gave you already a flavor that this formula already fits to the formulation of FFT, but we still haven't explained what is FFT and why this is beneficial to use that. So this is the objective of this block. So already what we have seen that at this point, once we have n dimensions, n grid points in x and u direction, this means that we need to have around n squared complex multiplications. Complex, it also makes it more difficult. This means that you have not only a real part, but also you have imaginary part. That's computationally rather expensive. And this is what we note by big O squared notation. In 1965, Cooley and Tukey have shown that it is possible to reduce number of evaluations for discretized Fourier transformation. A number of operations can be reduced really significantly. Then we have only n log n operations. To give you a feeling about how big difference it is, this is a graph here, a figure presenting red line shows you n log n operations, so depending on n. And then here we have a blue line, the green line, which is n squared or x squared. So you see that once the dimensionality number of grid points increases, we have a quadratic growth in a computation. However, if we have n log n, this means it's not linear, but it is not far away. It is definitely much better what we would have for n squared operations. So you can see that this complexity, it is definitely something that you would like to achieve. And this is already, maybe surprisingly, this has been already determined in 1965. And that is basically this application that what of Cooley and Tukey they have found. This basically constitutes the fast Fourier transformation that is used until today. So let us look at the details. So again, we start with a grid, two-dimensional grid with a grid for u and grid for x. We can also write our Fourier transformation, what we have derived so far, in the following notation. We have a matrix M, and then this matrix, of course, will be two-dimensional, corresponding for every value of x. So this is what we would like to get f of x, and x is a vector. Then we have to have a two-dimensional matrix M for x direction and u direction, and the corresponding characteristic function. We can also write this is maybe a little bit handy, we can write our summation of all these terms. So you can see that right now we are focusing only on the term that we have obtained here, right? So we are focusing on this term here. We don't care about those correction terms, the boundary terms. We're only focusing on this part. You can also see it from the definition of the characteristic function of density, which is calculated from the characteristic function. So if we look at this expression, we see that we have E minus IU x phi of u, and this is what is considered in the first derivations for FFT. So you can see this is this part, right? So we have E minus 2 pi I n minus 1 k minus 1, and this is what corresponds to our term here. We have E minus u 2 pi n minus 1 k minus 1, and then we have some function, right? So this is the function that we would like to use in our computation using fast Fourier transformation. So this is our function, you can call it phi n. If we do certain substitution, so this 2 pi I divided by n, it's not really helpful here, or minus in minus term, we can redefine this expression using omegas, and this is the definition of omegas, it's E minus 2 pi n. And then our matrix M that will be used for computation, it is of the following form. So you can see every entry of matrix M and K, it's given in this way. And what actually what is the greatest advantage of fast Fourier transformation is that you can see that the terms, so you have a diagonal here, the terms which are on each side of the diagonal, they're actually the same terms. And that's basically the key element for determining fast Fourier transformation. By using the symmetry of the terms, we can actually reduce significantly number of operations that need to be used for computation of Fourier transformation. So if we go further into details, we see that fk, it is in this new notation, then we have number of terms. We have 2 to the power L, and this is an even number of terms that we have. What we can also do, we can define our grid we can split into pieces, because of what we have just noticed is that we have n minus 1 n over 2, and then we have x, n, and y n terms, and those will be corresponding to those terms. So you can see that actually it is equivalent representation what we have here. So we divide it in odd and even terms. We have summation over two of them. Now, of course, since it's odd and even, we can actually use this fact what we have just noticed about the symmetry in the matrix. So let's go further. The basis, like we just said, behind the FFT is the symmetry, the similarity between the terms in the counter on the opposite side of the diagonal. And this is the property what we can use. So you can see that in the representation above, we had the summation of x and yn, and we can actually substitute. So there is you see omega n 2n minus 1 k minus 1, and we know that this is closely related to this term on this side, and this is the relation, right? So it's 2n minus 2 k minus 1 n minus 1 k minus 1. So, but because we have here, there was a 2n minus 2, and we have a 2n minus 1, we need to have correction term, and this correction term is basically here. So if you will multiply it here, 2n minus 2 and k and minus 1, you will see that we can actually represent in the same terms as it is here, right? So it's a n minus 1 k minus 1, but before we had 2n minus 1, as you can see here, was a 2n minus 1. However, what we see in the relations 2 and minus 2, so we need to have this extra correction term that we take outside of the summation. So then actually you see that once we divided in our summation into odd and even terms, and we have x and x ends and y ends, our weights are actually now given the same way, the same formulation. This allows us to represent this problem into zk plus, this is the additional correction term that we have just rederived from here. Of course, keep in mind that this omega n is exponential, so everything can go outside, obviously, if we take it a product there. So then we have omega n k minus 1 times yk. So this is a term that we will get from here. And then we can write the system of these two equations of fk and f. And then for this equation, once we choose k, actually we can substitute, this is index, so it's running index. So if we change k to k plus n over 2, every index will be also changed, as you can see. And this will essentially lead us to so-called butterfly relation, which allows us to reduce number of computations that is necessary in this algorithm. I didn't spend too much time in providing you all the details regarding the fast Fourier transformations, all those derivations. You can find the literature. Here, the key point is about the symmetry, the similarity of terms which are in a matrix. So once you have to perform multiple, the same operations, typically by reducing those, by using the similarity properties, you can significantly reduce number of computations, and that's basically what's the essence of fast Fourier transformation. Another takeaway is that once you want to apply integration and you want to use fast Fourier transformation, the key element here is that we need to find a special representation. So let's go back. We need to have it in special form that our FFT algorithm, so fast Fourier transformation algorithm, would digest. So as you have seen before, we played a little bit with parameters, with the settings regarding the mesh sizes, the grid sizes, especially this was about the relation between a number of grid points in x direction and u direction. This was why this 2 pi over n came out. And once we want to use FFT, we need to have this formulation in a special form. Then we are actually allowed to do that. Also, another takeaway, in this representation, we have used trapezoidal integration. So I provided you the details about that integration. However, keep in mind that there are multiple ways of integrating a characteristic function, right? So if you like to recover density, you may go for Simpson's quadrature or even much more advanced numerical techniques. However, if you like to use FFT, then every time, whenever you choose particular integration routine, you need to go through the process of formulating in a way that that the Fourier transformation, the fast Fourier transformation, is applicable. So this is something to keep in mind. Okay, if we go further now, let me look. So you see that this is a manual I have taken from SciPy regarding FFT, and you can see that if you like to apply FFT, this is exactly the same form that we have derived. So it's a summation, and then we have an exponent. You see that's an exponent of minus 2 times I times pi times k, and then we have also n direction. So you see it's a k times n. So in our case will be direction of x, direction of u, and then we have divided everything by n. So this is exactly what matches our representation, what we have done once we apply trapezoidal integration for recovery of density given the characteristic function. So now let's perform as an experiment. So we consider the simplistic case where we have a Gaussian distribution, Gaussian random variable. For Gaussian random variable, we can characteristic function is known analytically. So it's an exponent, and we have a minus, so I mu u minus half sigma squared u squared. Of course, we can choose different set of parameters. I have just taken here mu constant and sigma 1. It doesn't really matter. What we would like to see is how to perform coding of this FFT, fast Fourier transformation, and how fast it is. So let us take a look into code. So code consists again of two blocks. So we have a main function where we specify some configuration. So here we have mu and sigma. Those parameters will be changing them and seeing the impact of those parameters on the recovery. Then we have a lambda expression for the characteristic function. So it's a function holder, an exponent, and this is the formula that we have just seen in the slides. Here we define a domain. So given this distribution, normal PDF, this is what we would like to see. So we specify we'd like to see PDF from range -8 until 8. So this is the input that we see. And for given this input, we would like to recover our density. And for that, we call function recover density, where the first input is characteristic function. So this is the affine here. We have x which is the grid at which we would like to calculate this density. And the third argument is the number of the points. So this is number n. So it's a number of points that you use in our transformation. Okay, so details regarding the recovery density function. So we have three arguments. As you can see, that there is a default setting for the third argument. So if this argument here is empty, so just leave it empty, then the third argument will be taken default. I think this is 8 to the power 13 as the number of grid points. You can see those points are rather large, and that's rather typical for Fourier transformation. Those grid points they need to be large in order to recover density, high accuracy density. Later in this course, we will learn about Gauss method, which requires much fewer expansion terms, or you can say grid points in this way, but this will be for next time. Okay, first of all, we define I to be a complex number, so it's a complex 0, 1, so it's only the imaginary unit that we have. We define the domain, the maximum, so this is the U max of our integral. This is a parameter, and that will be chosen according to when, like we have seen, spinning of the characteristic function goes to 0 and it's irrelevant. 20 at this case, it's rather safe. It's normal distribution converges rather fast. This is one of the parameters that you don't change too often. 20, I think, typically is good. If you have a very peaked distribution, this means that it's not, let's say, it's not Gaussian, but it's very much condensed around 1 point. Then this U max will need to be much larger. We have also a du, so the grid size. So this is delta U that we have seen in the lecture notes. Then we have a U max divided by n. So this is number of maximum divided by number of points. And here what we do, we define a space, a grid from minimum until maximum. Minimum obviously is 0 because we use the inversion lemma. So inversion lemma allowed us to reduce the space from minus infinity to plus infinity to 0 infinity. And this is what we also use here. And then we define a grid until U maximum. The dimension for x, maybe you remember we have this free parameter b. In this case, I'm just choosing b to be minimum of the input that is put. So assuming that you have a good grid of you would like to recover full density, then the b parameter will be the lowest part of it. It will be very far away in the left tail of a Gaussian distribution. This is if you recover a density and something goes really wrong, or the density explodes instead of decaying in space, then very likely you have to change this parameter too. Again, now in this case, we use this relation between dx and du. Remember, dx times du was equal 2 times pi divided by n. So this is the relation that we are also using here. And of course, given minimum, we have a grid now. So it's a minimum, so b plus n space with dx spacing until number of grid points is reused. Okay, then characteristic function. So we have a phi. So it's here we call the input characteristic function, and we multiply with minus bu. So this is something that we have seen already. So this is the Fourier transformation we apply to this function. We have 2 boundary points for first and the last point. So you can see here. And then FFT, we do du divided by pi times real part of the Fourier transformation of this function phi, and then minus the boundary that we have, this boundary condition or the boundaries of the trapezoidal integration. Given that, so at this point we will recover the density, but only at the grid points, so only at the points that they were calculated here. So this is the spacing we have defined. So in order to make it sure that if the input here x is not in the grid, we have to handle some interpolation. So here I define a cubic interpolation. So we define a grid xi and fxi, and then we evaluate our inputs x at those points. So imagine if you have, for example, here, let's say 8,000 points. However, your input x involved 1,000,000 points. then we would still perform the fast Fourier transformation on 8,192 points. However, the remaining points, which are actually needed as the output of the function, those points will be just interpolated using cubic spline. So you can see this is also beneficial. We always know that if your x is very large, you'll be always limited to the Fourier transformation, and then the remaining part, the time necessary for calculation, is not going to go anymore to FFT, because that is always fixed. This will always go via interpolation, which is comparably cheaper than actually doing fast Fourier transformation. Maybe n-log n operations is low. However, if your number is very large, then you may really lose the benefits of having fast Fourier transformation. This is for that reason interpolation is commonly used. And once we have this, we can just run code, and we see here the comparison of a PDF from exact. So the exact we also have defined here. So this was, let me see. So exact density, as you can see, is defined here. It is just taken from the library. So from SciPy, norm, PDF with the parameters. And then for the recovery, we just calculate ourselves. We can also play with parameters, of course. You see that's rather fast. And number of maybe what we can else we can change sigma, make it larger. You see it's getting wider. Then if I make it very large, let's see if I can destroy it. Let me see. Maybe we can expand the space here. 18. Let's see if that will. Or maybe let's make it -1 to 1. Maybe that will be something can ruin it. No, not really. So you can see it's rather reliable in the current settings. Maybe number of points. Yes, you see it works very well. And for the input parameters that we have chosen, you cannot really destroy this function. I think if you play with number of number of points that are used in a Fourier. So for example, here we do not the default number of 8,192, but we will do let's say 10. Let's see if this will work. It still works. Just do here 100. Okay, this works well. Let's see the lower limit. Let's say make 9. Here 2 to the power 8 points, 2 to the power 7, 2 to the power 6. Okay, you see now it's already some problem appears with the interpolation. So, however, those problems may appear. This is related to that your grid, the space of grid, was smaller than the maximum x that was asked. So this is, let's say, a detail that needs to be taken care once you are developing for production. Let's say if you work in industry, you have to make sure that all those things are nicely handled. Here is just illustrative case, and I hope it is sufficiently clear. There are few takeaways once we talk about the cost method and why the cost method is very handy and it's very useful method. The first of all is that it allows for exponential convergence. This means that in number, cost method is basically an expansion technique, so that we don't build a grid like we did for fast Fourier transformation, but we have just iterative process of calculating option prices and also iterative process in recovering of density. If we have a number of terms in that expansion, then the technique converges exponentially in this number of terms. Another great advantage of the technique is that Greeks are obtained at no additional cost. This means that we don't need to calculate, let's say, sensitivities using finite difference by, let's say, shocking parameters and reevaluating. We can do it directly using characteristic function. So if you have a Heston model and you like to calibrate the Heston model, maybe your optimization would require that you also provide gradients of option prices to all model parameters. That is also a possibility, and this is a rather popular approach. For that, you could also use cost method that would provide you all the sensitivities essentially for free, or at least not higher price that you would pay as you would like to, or that you would pay for calculation of option prices. So there is no additional costs. Application of cost method can be also used for pricing of more exotic derivatives, like for example, discretely monitored barrier and Bermudian options. So these are the two, let's say, advanced payoffs that can be also used, can be priced with this cosinus expansion technique. What is the basic idea? The first idea that you can, when you think about cosinus, like I just said, it's a series of expansion, so it has a it's kind of iterative process when you add extra elements in your sum. So this is something like you can think of a Taylor series where you have number of terms, and more terms you will have in your expansion, better the quality of the approximation. Another thing that is very important is that the series that you have, it's very much related to characteristic function. So this means that if you are recovering your density or calculating option prices, you can simply make a use of characteristic function, and you don't need to perform any additional integrations or computations. Directly, cost method allows you for direct relation with a density of the characteristic function. So there is a one-to-one correspondence without additional integrals. Let us start deriving the cost method and giving you all the principles about all the steps how to derive it. I would like you to refer to the book if you like to see all the steps in between. All the details are also provided there. Today I will just give you a helicopter view on the methodology and the main idea. The relation, of course, this is the famous relation we have already seen multiple times. Characteristic function is simply an integral of e minus y u, and then we have a density, and then we have a density, and then we have to do an inverse, and so 1 over 2 pi, we integrate, but this time we integrate characteristic function. So you see there is a one-to-one correspondence. You can see this is here, this is there. So if you want to switch from one to another one, you always have to perform numerical integration. In the previous block, we have learned that if you like to recover density using characteristic function, then we can simply do a fast Fourier transformation, and that's very advantageous. Okay, Fourier series are just expansions, so it's a it's a Fourier transformation is basically an infinite summation consisting of two terms. So if we have a function g on domain -1 to 1, we can express it as function g, and then we have two sums. Keep in mind that if you see a prime in a sum, this means that first term is always multiplied by half. So this is something to keep in mind. If your code, once you implemented cost methods, and your code has doesn't converge or something is really going wrong, then I'm pretty sure that the first thing you should check is whether you multiply the first term of your expansion with half. Okay, so we have a summation consisting of two terms. We have a's and cosinus and b and sinus, and this is support on -1 to 1. So as you can imagine, once we talk about the recovery of densities and we have Fourier space from the characteristic function, this domain definitely is not enough. We need to change the variables such that it will cover the whole range of the integration range that we are interested in. A and B's, those are just coefficients. So you see that the function g of theta, it is expressed in the summation, and each coefficient ak and bk is given by integral. So once you look at this representation, it doesn't look very handy, because you see, you can read it as follows. If you like to have a function g, then essentially you need to calculate integral of function g. So that you can see that this is not really handy. However, in the cost method, these relations are nicely found using the characteristic function, but this will be details later. But this is essentially the relations of function g. It's infinite sums of integrals involving also the same function. So that's the equality relation that you have. Of course, number of terms has to be infinite. Otherwise, I mean, in practice, we would just truncate the summation with a particular number of terms. Of course, we have a cost method, so you can imagine that the sign expansion is not of interest, so we choose bk coefficients to be 0, and then we obtain a classical Fourier cosine expansion. So it's a cosine in this, this is actually the name of this method. It's a cost method, which comes from this cosine expansion, by which we can represent even functions around 0, theta equals 0 exactly. This is now we have a simple trick how to make sure that we always have, if you have a function on support 0 to pi, how to make sure that we have even functions. This is simply by switching the arguments depending where the arguments are. Even functions can be expressed as Fourier cosine series. So this is our starting point for deriving of the cos methods. Okay, as we have seen before, on the support of minus pi to pi, we have the following expression for the cos methods. Function g is an infinite summation with half of the first term, ak times cosinus k theta, and then expression for ak is given as 2 times pi 0 to pi g theta cosinus k theta d theta. So as you can see, again, we have this relation that expression for function g also depends on integral of this. So this is, at this point, there is no really direct relation. If you like to recover, for example, density, this equation would tell you, okay, if you want to have a density, you need to integrate density. So that at this point is not really useful. There are a few details here, but what is the most important thing that we have to do first is that you can see that we are integrating from 0 to pi. We need to change that domain by changing variables. We need to have integration happening from a to b. And this is what we do here. If we would like to have a finite integral, so if we like to have a finite support a and b, so those are the parameters we choose for our domain. Of course, they are in R. Then we have to perform some change of variables. So we change variable theta to be y minus a, b minus a times pi, and the same we do for y. And this allows us to integrate or recover function in a specified interval. So this is the first step. Instead of bounding ourselves to minus pi to pi, we have a integral range from a to b, and you see that there is some additional scaling that takes place in the integrals, in the cosinus, and this is due to the fact that we have changed the variables according to the specification here, right? So function g, we have summation of coefficient ak, and ak are given here. Right? So this is a set of equations. Okay, if we go back, of course, at the end, what we are interested in, we are interested in recovering density using characteristic function. So this is the key element of this method. So if we look at the characteristic function here, which is given in terms of density. So what we have done first, we have a truncated domain. So you can see it here. We have first we have a hat indicating that we have our domain for integration domain is truncated. This is very practical. Otherwise, in essence, it's difficult to have infinite summations and infinite integrals, of course. Those points A and B will be chosen in the cos method itself. Then those points will be given specified. If we, for example, know the cumulants of the density, those parameters can be easily found. However, there are also some heuristic choices how to choose those points. There are also some ranges that you can just pick up, and then you'll be fine. Okay, one thing, okay, so this is the integration. Of course, this is an approximation. What is very important in these derivations that will follow is the famous Euler formula, which says that an exponent of iu, it is simply cosinus of u plus I sinus u, and I is a complex number. And once we take a real number of EU, then we end up only with cosinus part. So this is also very important. See, then the imaginary part is completely gone. Okay, so if we have a random variable x and we have a which belongs to R, we have characteristic function of u times e to power I a. Then definition of course, the expectation, the definition of characteristic function with additional coefficients that goes under the expectation. Then we end up with an integral minus infinity to plus infinity, and then the following relation. This is just an application of definition of the characteristic function. Okay, if we take a real part of this term, we will see that we can actually, so the density is not affected by taking real part because it's a real. Real part can also go under the integral because it's essentially a summation. And then this expression here just becomes in a real, if we take a real value of it, it becomes only cosinus u y plus a. Now, if we do the following, so if we substitute u with k pi divided by ba and multiply equation 13 by some exponent, so this is very important. If you multiply this equation by exponent, we end up with the following expression. So here we have then characteristic function of k pi b minus a times exponent, and then we have this expression for evolving the density. And what is important, if we take now the real parts from both sides, so real part of the left-hand side and the real part of the right-hand side, we end up with a very interesting relation that you remember in the, once we talked about Fourier expansion, the function that we want to expand also dependent on a function of a target, right? So this, you remember maybe here that we had a function g, that expansion of approximation of function g required that we integrated function g here, right? So that's basically what we have seen. However, once we do the substitutions here, that I let you look at it in detail using book, for example. But once you do the substitution, you will see that actually we had also the recovery of density also involved integration of density, right? This is exactly the same as we have seen in the definition of the Fourier series. However, because we have this relation of the Euler formula, this integral actually can be expressed as the real part of the characteristic function. And this is very beautiful. This means that actually, instead of calculating this integral from a to b of the density times cosinus, we can actually take a real part of the characteristic function scaled with the exponent coefficient. So you see that this is essentially, this means that if we have this formula, instead of using this integral of g that is necessary to calculate this expansion, we can actually make use of the characteristic function, because this will be just a function of a real part of some characteristic function scaled with some exponent, right? So this is obviously something that we have because we are working with Fourier spaces without the characteristic function. So obviously this is something that we have already, we can use it. And obviously, this is something that we would like to have. So the cost method is about finding those nice relations between integrals of the target function and the characteristic function using the definition of the characteristic function. So this is very, very elegant and very, very fast at the end also, right? Because it saves us a lot of time if we think about those integrals. Okay, so if we think of those coefficients, so coefficients fk, so we have approximate, so ak was the coefficients once we had integral from minus infinity to plus infinity, we approximated with fk, which has a domain of a to b, so those coefficients are here. So essentially, if we talk about expansion, so if you would like to have a density, this as a summary you can think of, it's a summation from k to 0 to infinity, or of course with some n plus n minus 1 terms, fk, and fk is basically a real part of the characteristic function with some cosinus. So this is actually also why this cosinus method, why it's called, is basically you calculate characteristic function, you have characteristic function, you take a real part of it, you multiply with a proper cosinus term, and that gives you approximation for your density. There are a few takeaways once we talk about cost method. The first one is that in the method itself, we have introduced an error which comes from infinite summation. So maybe you remember in the cost method, we have a finite number of expansion terms. That is also a source of one of error that we have in the method. The second error comes from the truncation domain. So in the recovery of density, we have specified A and B that need to be chosen. And of course, since we don't cover infinite domain, that also is a source of error. So this is good to keep in mind that the method, although very handy and very fast, it is still, there is some error that can be generated. However, the cost method is also, it's called so-called entire functions method. This means that once the function that we are recovering doesn't have any singularities, then we have convergence, which is exponential. And that's also something very, very important. This means that even if we have specified some range on without singularities on a range of A and B, with a low number of expansion terms, we can have extremely good quality results. So this is something that to keep in mind. We have errors in the cost method, but those errors are easily to be controlled, and they are the method does not require many terms. As you remember in FFT, once we were recovering the density, we needed thousands of grid points. So we had this two-dimensional grid, which involved many terms. In the cost method, this is not the case. We achieve very high accuracy even for few terms. And that will be present. That will be very clear in a few minutes once we look at Python code. Okay, to summarize, this is the summary of the Fourier cosine expansion. We start with a density which is expressed as the infinite summation from n equal to 0 with a half of the first term of terms fn cosinus, where fn is given as some integral of a density, and then we have also product with a cosinus. This term, fn, can be approximated by an, which is essentially a truncated integral, or the integral in this case, as we can see, it is actually a real part of the characteristic function. So you can see we translate this integral into the real part of the characteristic function scaled with an exponent. And this is the greatest benefit of the cost method. Okay, now let's take a look at some experiment. In the numerical experiment, we will consider, again, normal PDF, sorry. So normally distributed random variable, so with the following PDF, and of course, this will be a characteristic function. In the experiment, we define A and B to be minus 10 and 10, so this is domain of our distribution, and we are interested in values of PDF at given points. So we have a -5, -4, until 5. In the experiment, what we're doing, we'll be checking, okay, what is the error that we generate depending on number of terms. And then we also measure the time. So this is the objective here. As you can already see from this table, is that once we have 32 terms in expansion, accuracy extremely good, because we have error of 10 to -7. If we have 64 terms, we are already approaching the machine precision level, so 10 to -17. Let's take a look at the code. In the code, we have an experiment which will also, again, consist of two blocks, the main part and then the cost method part. First of all, we specify configuration, so domain, integration domain. Here we have a range of number of expansion terms. So this is, let's say, a fancy, a Pythonish way of writing n to be a vector of elements. So we have 2 to the power x, where x belongs to this range. So this vector will have exactly number of terms that we had tabulated previously. We have a mu and sigma, which come from normal distribution. These are the settings for normal CDF or normal PDF. Here we have a characteristic function. Of course, the characteristic function is also mu here. We have sigma. So everything is, as we have seen already before, we have a number of x's. So this is this domain, x domain, that we have from -5 till 5 with 11 elements, because we also include 0. We have a reference, which is f exact, and this is just the exact normal PDF. And what we do here, we have a for loop for every n in a vector n. So for every number of expansion terms, we'll be looking at, we were generating density using the cost method and defining error as the maximum absolute difference of a density which is exact and density which is recovered using the cost method. And of course, this will be for all the x's. So this error will be computed at the range of x. So we will take only the x which gives the biggest error. This first part, and as you can see in the cost method, once you want to recover density using the characteristic function, it's only few lines. The first line, of course, is define complex number. Then we define a grid for number of terms in the expansion, number of arguments for the characteristic function. So this is, you can see this u. It is also a parameter specified. It's a scaled parameter. So remember, maybe we had k over times pi, and then we had this range. So this comes from the scaling, the variable change in the integration. And then we have coefficients, which are, again, this is a constant part. times real part of the characteristic function multiplied with an exponent. So this is the key. Let's say this is the heart of the cost method. So this part where we connect the coefficients with characteristic function. And then something not to forget is that first element has to be adjusted to multiply by half. And then at the end, the final calculation that we just performed summation of all the terms. And here I did in the matrix notation so that we have the fast calculation, so we can do it for multiple x's at the same time. Okay, so once we run this code, we can see this is performed for all the, it's a for loop, right? So we have for number of expansion terms, we have error. And here you can see that number 4 terms, we have 0.25. But if you go 32 terms, we have 10 to minus 7. And as already we have seen, 10 to minus, for 64 terms, we already have 10 to minus 17. This is very good. If we, of course, we can also play a bit and expand number of space of the arguments. Here we can have, for example, 100 x's. You see the density, it immediately improves. So I think this is how we can look. So the blue line will be the one with the 4 expansion terms. Orange one will be 8. And then we have a 16, which is already close. This is the one with oscillating. 32, it's almost on the top. And then 64 is basically the best. You can see that once we have here, now the error actually has increased once we have increased number of x's. But this is just, we are playing on the boundary of the machine precision. So at that area you may not see improvements. Let me see what happens if we have 1000 terms. It's still 10 to minus 16. Let's try also to expand our domain. So it's a minus 10 to 10. Let's see how this will affect the results. And you see that there is, maybe you can see a little bit more oscillations for distribution, for density, with fewer number of terms. And this is something that is also present in the cost method, that because it's an expansion, you may also see some kind of a Gibbs phenomena. This means that if you have insufficient number of terms, there could be some kind of oscillatory behavior sometimes, especially if you have some kind of density which is rather peaked. But this is something that it's inherited in the framework. What to keep in mind is that you have still few parameters to tune, so it's not ideal. A and B are 2 parameters, so you specify domain of your interest. And most of the cases you will know the domain that you would like to get your characteristic function. What is the integration domain? Sometimes you may use also some properties of the distribution beforehand to calculate these numbers. Later, once we talk about pricing, there are some good heuristic choices for A and B which work most of the cases. Another term that you always have to keep in mind is that you need to specify number of expansion terms. So this number n. In this case, 64 was enough, but once you deal with distributions which don't resemble so much nice bell-shaped, but they are heavily tailed, then 64 maybe not enough. Maybe you need to use hundreds of them. For example, 500. That's a number which is, I would say, on the high end. So this table presents what we have just seen in numerical results, that we have for 64 terms, we have around 10 to minus 17 precision. For 32 terms, we have 10 to minus 7. So this is what we have just reported in the numerical experiment. In numerical experiment, however, we haven't shown the time, but you could see that performs very fast. And this, you see 0.29, this is in milliseconds. It's not even seconds, it's milliseconds. And this is also the graph that we have generated. So depending on number of terms, we could see better behavior of the density. So more terms we have, less oscillations we have, and then the quality of the fit becomes it's better and better. We can also look at log normal density. So we have seen normal case, but we can also do log normal. But for that, of course, log normal density on log normally distributed random variable doesn't have a characteristic function, but we can still make use of the normal characteristic function. And this is how it goes. So we know that there is a CDF relation between normal and log normal, and this is what we can do. The CDF of y, which is log normally distributed, it is by definition probability that y is smaller or equal y. This means that we have e to power x, where x is normally distributed, so we can take a logarithm. So we know that at the end, using this relation here, is that CDF of y at y is equal to CDF of x, where the argument is basically scaled with logarithm. And this is very nice. Yeah? So you can see there is a relation between normal and log normal. If you look at the density, we have to differentiate, of course, the CDF, cumulative distribution function, and then we end up with the following relation. The density of a log normal distribution is equal to 1 over y, and then we have a density of x logarithm of y. So let's take a look at the code regarding log normal case. So we have specified number of expansion terms, but because it's log normal distribution, we need to have a higher number of terms. Again, we have some parameters mu and sigma, and then for number of expansion terms, we perform calculation of the density. But as you can see, we do this time slightly different. So our density at given argument y, it is given by 1 over y times cosinus. So this is the density that we recover for a normal distribution, where we provide normal distribution here as the lambda expression, but arguments that we give to this function, they are logarithms of y. So this is slight difference. And this is actually exactly what we have derived in the slides. So if we run this code, we see that the results are much different than what we have seen before. We see that there is much more oscillations, especially around zero. So this is this phenomena which I have just mentioned, is that once we are at some kind of singularity, then the oscillations may be present, especially if we don't have enough number of terms. So you can see that here we have a blue curve was for 16 terms, so it was completely away. Even the density, recovered density, was negative. If we have 64 terms, this is the orange line. Although 64 terms is perfect for a normal distribution, is definitely not good enough for log normal distribution. And then once we had twice more, so 128 terms, we see that the blue line, the green line, it nicely fits. So you see, once we have a distribution which is not normal, we need to really take care that number of terms. We don't keep it at very low number. Number of terms should correspond to the type of distribution we are dealing with and what kind of domain it is. So for normal distribution, we know that's infinite domain, so minus infinity to plus infinity. For log normal, we know it's from 0, so that means there could be some kind of oscillations around area of 0. You can also see it by this term here. We see 1 over y. You can expect that once you put y close to 0, this number becomes very large. So of course, depending on the term what you recover there, but that's something to keep in mind. If I see somewhere division, then that's always something that is alarming, and I always recommend to double check. Though the cost method is very powerful for recovering density once we have given a characteristic function, in finance we are mainly interested in derivative pricing. So now we focus on application of the cost method for pricing of European type options. So again, European option is an option that only has a payment at the maturity. This nicely fits to recovery of density, because in a density we also have only one given marginal density. So once we think about pricing of a payoff, essentially we are integrating a product of a density times the payoff function. So this is what we see here. So we have a value at time t0. It is some discounted payoff. So here we use a delta t is defined as capital T minus t0. So it's a, of course, case of deterministic interest rates. However, in a it is not necessary condition that we have deterministic interest rates. In general case, as we have seen already in a affine diffusion framework, interest rates also can be stochastic. And now we have expectation under the risk neutral measure. This means that the density that we are using here has to be under that measure. And we have a payoff function of y. So y in this case is our stock density, or the density that we have recovered from the cost method. Then this is equivalent, of course, that we have an integral over the real part, over the real axis, of a payoff function times the transition density. As I already mentioned before, here the transition is from time t0 until the maturity time t. So it is maybe mathematically correct, but in practice we always consider time t0. So it's essentially a marginal distribution. Later we'll be talking about more exotic payoffs in which we can actually derive characteristic function and we can use cost methods once we talk about distributions that they are actually transition densities. So for example, to illustrate this on time axis, once we have t0, we know that t0, it means that at this point, initial value of our stock is known, it's just a number. So then we can consider a step to maturity time t. However, if we are here, but we are interested in a transition density of t1 to t2, then obviously the initial point here, it is not known. It will be known once we get to this point. So at this point, you can say the initial value is given in terms of a distribution of a random variable. And for that matter, the formulation of the cost method is slightly more involved, but details on that I'll provide you later. So, okay, so this is the essentially definition. Then we go into cost methods. So we have a truncation of the density. So the density is here. We cannot, in the cost method, we have to define truncation of the density. So we have some interval A and B, and we have epsilon. So this is epsilon, make sure that we have an equal sign here. Otherwise, if you wouldn't have epsilon, it would be just an approximation. As you can see already from the cost method, we can simply substitute the density that we have already derived. So density was derived in terms of summation of a real part of characteristic function times some exponent. So we can just simply, this was given in a previous slide, here we can, the density is given in this term, so we can substitute this whole expression into that integral. So essentially we'll be integrating, this will be summation of integrals of coefficients times cost terms. So this is what we actually see here. We have a summation of real parts of a characteristic function that depends on x. Then we have exponent, and then we have I and pi a b minus a, and then we have this coefficient hn, and this coefficient hn will include the integral from this expression here, because we are integrating over this density, so this hn would need to compensate, we actually need to represent that integral. Yeah? So this is essentially the what is also important here, look, that we indicated the initial step is x, so it is not part of that integral because this is essentially our value s0, which essentially it's also important to notice that this x is given here. So it's important that characteristic function is given in terms of that x is conditioned in phi. But let's go into details. So how to derive it? Of course, this coefficient h here, it will depend on the payoff. So whatever we choose for v, whether it is a European option or call type, it's a call or put or digital option or whatever you think of, that will have direct impact on this coefficient hn. But I will show you just in a next slide that whatever payoff you will choose, this is a rather generic representation, and the integrals provided here will be much more that you could apply in multiple occasions. So let's see. First of all, we have to define adjusted log asset price, which essentially means that our stock or new variable y, it is given in terms of a logarithm of a stock at the maturity divided by k. It's kind of a scaling coefficient. This will be later also very helpful once we talk about the vectorization, because at the end, we are interested in evaluation of call or put option prices for multiple strikes. So as you can imagine, in market, we have strikes for we have implied volatility smiles for multiple strikes. So we would like to evaluate the whole smile for all the strikes we have. We don't want to repeat cost evaluation for every strike. So this is also very important, especially once we talk about calibration. Okay, so then if we have this representation, our payoff looks as follows. So you can see that there is this alpha bar, which is either -1 or 1, depending on a call or put option. And then we have a slightly different representation, but it is nothing different than what we had before. If we substitute here yt here in this term, you will see that things will nicely cancel out. So exponent, we have a logarithm, this will cancel out. Then we have a ratio of st over k, and this will cancel out with our k, and then here also will be k. So essentially, this is just a different representation of a payoff. So once we have this representation, you can see that we need to calculate integral over this payoff function times the density. So this means that we have an integral from basically this is a payoff that we have there, right? So this is a payoff function, and then we have cos of these terms. So cos of k pi y minus a b minus a, and this term comes from this cos representation for the density. So this is presented in a previous block. And if you, this representation actually, because we have a minus sign here, we can decompose in two elements. So we have a k times e y times cos, and then we have a k minus k times cosinus. So of course, k is constant. It can go outside the expectation, outside this integral. Then we have a essentially difference of two integrals. So this is represented in this generic form. It will be psi high k and then psi k with some boundaries a 0b 0b, and for put option, so essentially for alpha equal to -1, then we have slightly different representation, but again the same functions. So of course the key question is how to calculate those integrals. Integral of 0 to b ey times cosinus and 0b -1 times the cosinus. So then we have actually this representation, and then we have a second representation here. So you can see this is the one which corresponds to e to power y cosinus, and then for psi we have 1 times cosinus. So this is actually this representation, it comes from here. So this integral will be decomposed in two, and those are generic for different coefficients c, d, cd. We can basically freely choose them. So in some of the payoffs, you may choose c equal to a, or as given here, depending on the coefficients that you will specify. Those are generic functions for those integrals. So this is why here we have a 0, 0, and then here we have a0, a0. So we reuse those coefficients depending on a payoff that we have to calculate. So you can see for calls and puts, they have slightly different arguments, those two functions. Okay, and this is, of course, those integrals we need to still calculate. Otherwise, it will be a little bit of problematic, because every time you want to evaluate this, you can see that this function depends on k. So essentially means for every iteration or every summation term, we will need to compute this integral. So if this integral, every expansion term has to be computed numerically, that will be very expensive. However, those integrals are not really involved, and you can find them analytically. It's a little bit maybe a long expression, but you see it only involves sinuses and cosinuses, so it is rather straightforward. You can check it whether it is correct, but I'm ensuring you that this is fine. Here, of course, you have to make sure that the psi function, it will change its representation depending on strike. So for the first term, you have a d minus c. For any other term, you will have this expression here. But once you implement this once, you don't need to, you can basically forget about it. It will be always reused in your representation. On the other hand, you can also see that you can evaluate those functions for multiple elements k, right? So this is basically, you can evaluate for whole vectors of k. You don't need to do it as the for loop. You can just do it in a whole vector. Finally, is the time for implementation. A very important aspect of the cost method is that we are able to implement this technique for multiple strikes. This is in particularly very important once we talk about calibration. In multiple asset classes or stocks or commodities, there is not only one strike, but could be, let's say, 10, even 15, or even more. Then this means that we don't need to repeat our cost method for each individual strike, but we can just do pricing for whole strikes, all the strikes in one go. So this is the important aspect of the cost method. So maybe you remember in a previous slide we had already those functions depending on integration ranges, A and B's. Those are the high K and the psi K. We can just simply say that these are UKs. You implement once them, and then you keep you can always reuse them. So our pricing we can actually represent in this following form. So we have a PK coefficient, which is matrix UK, a vector times the vector of K, but this will be clearer a bit later. What is important in evaluation that we want to vectorize elements. So here, this is basically the key implementation, the formula for implementation. We have K here will be a vector. So here we can, our K, it will consist of, let's call it nk elements. So nk times 1. So this is our vector here. Then we have this element, which will be a matrix. Matrix consisting of nk times n elements. So we will have it's a n starts from 0 to n minus 1. So we have n terms of the summation, and we have a nk strikes. So basically we have each row corresponds to each individual strike. It's the same as here. And then here this element is basically is essentially a vector, of course, with n expansion terms. So if you have essentially we can just perform a product of those two matrices. So it's a matrix times a vector. Then we end up with a vector of size nk times, this will be times 1. So we have a times 1. And we multiply with a vector nk times 1. So at the end, the output will be a vector of size nk times 1, corresponding exactly to the number of strikes that we have used. So this is basically a sketch how we could implement. Of course, we need to calculate some real parts, and we have to make sure that everything is handled properly. I will show you in a few seconds how to do implementation in Python. Maybe one more element here is that once we have this function phi, so you see that there is a characteristic function. Once we talk about it, this phi here does not depend on x. So this initial value of our stock is taken outside and is actually represented here. So this is rather important. So this fast representation for multiple strikes only works well once we have once we can decompose this x, take it outside of function phi. So you see this part does not depend on x, and here we can build a matrix that will depend on x and also n. So we have two dimensions. Here it's only a vector. Once this phi would depend also on x, then it complicates the evaluation. So this is something that is not going to be handled in this lecture, but in general there are possible models, especially when we talk about OU processes, then Onster-Unbeck mean reverting processes that could be much more involved. Okay, so this is yeah, this is I think this is enough to already to perform good implementation. Here is maybe one more remark. We have a function phi, and this is characteristic function that we have already learned how to derive it using the affine jump diffusion model. So once we have a model which is affine jump diffusion, and we have given a characteristic function, we should be able to represent it in this way, efficient way. Here's a small example about accuracy and convergence depending on a number of terms. So here we have some settings: initial stock, interest rate of 10%. It's a very high interest rate. Of course, these days it's very unrealistic. Q, this is something that we discuss more in the book, but this coefficient corresponds to the dividends that could be paid out. So, but you see it's 0, so essentially this is just the geometric Brownian motion that you're already familiar with. We have a maturity. Here it's already a bit short maturity, so this means it's a bit more challenging. So how to think about it? Once the maturity is very short, your distribution is typically much more peaked if compared to the distribution which is far away in time. And that a smooth distribution typically will converge much faster. So you can say this is not the super trivial case. It is a little bit more challenging. In this case, I would expect we need a little bit more terms to achieve good quality convergence. And then we have sigma, which is 25%. So this is a comparison. How much time does it take for each? So we do evaluation for whole vector of strikes, of course, and then we compare the result, the quality results, and this is the time necessary for the evaluation. So you can see that initially for 16 terms, it is rather bad, but once we have 64 or 128 terms, then we have very good results already. I would expect that if this t here would be larger, let's say 5, for example, 5, then we could get already good results for 32 or 64 terms. So larger maturity, this means that the distribution diffuses, it's less peaked. This means that Fourier expansion, we don't need so many terms in the Fourier expansion. Let us take a look at the code. Code is a little bit more involved compared to what we have seen before. Here's the main function where we do configuration, the main settings. So as you can see, we have initial stock 100. We have a tau, which is time to maturity, so it's a 0.1. We have volatility 25%. We define a vector of strikes. So this could be much longer vector. Now we just consider 3 different strikes. We have a number of terms of the expansion, and we have a L. So this L is a little bit maybe magic, cryptic. What is it? So this L, it corresponds to the a range for coefficients A and B. So this will be maybe clear later in the code. But this L is something that typically for jump diffusion models, we keep it at 10 or 8. That if you don't achieve good quality convergence, then this L coefficient should be cured. But once we go there to that piece of code, I will explain it further. Here's a generic function. So you can see it's a lambda expression where we define characteristic function. So in this point, we have just a Black-Scholes characteristic function, or for the log of Black-Scholes. And keep in mind that we have excluded this coefficient IUX0. So this is something that I already mentioned before. We have this representation for Levy processes where we decompose characteristic function into 2 elements. The element exponent of IUX times the rest. So this characteristic function here does not depend on x. You can see this is only u. So always keep in mind to make sure that if you plug it in for fast evaluation, your characteristic function should not depend on x. Then we have number of iterations. You can see that this experiment we perform experiment measuring the time. So we will just repeat the same evaluation multiple times and take basically the average over how many iterations we have done. This is a rather standard way of measuring time. So we don't just do one experiment and one run and then measure the time, because every time we repeat it, the time will be slightly different, because there could be a number of variables could be initialized, which is rather expensive, and second run or third run could be already available. So for that reason, also the slowdown of the system. So for that reason, we typically repeat, especially if the simulation takes very little time, then it's very advised to repeat experiment multiple times, many times, and then take average of the time needed for all of them. So this is what we do here. But you see that there's this coefficients here, they don't depend on number of evaluations. So we just do the same experiment all over again, just to measure the time. And here we do, because we consider Black-Scholes model, we know exactly what the option price should be. And this is what we do in this part. So we just call Black-Scholes model and we compare it to the result that we obtain from the cost method. So let's take a look at the cost method. So we have here we define reshape the metrics of the vector of strikes. So this is just to make sure that we have a column vector. We define a complex number. We have this initial S0. So remember this transformation we have used to derive those integrals for the cost method for pricing, which is logarithm of S0 divided by strike. We have a coefficients A and B. So those are the integral. So this is the range used for integration. As you can see, this L is actually now we have this present. So maybe you remember when I talk about the volatility, about the diffusion of the process, how this speed of diffusion how we can think about it in a, let's say, Black-Scholes world is typically volatility times square root of time. And here you can see that we have an integration range. It is basically a heuristic approach. The integration range changes 10 times the square root of time. So we assume very large volatility, you can think like that, plus minus volatility times square root of time. And this is rather flexible. I would say in most of the classical cases, it will nicely fit to the model. Once you tune those parameters, so if you find better A and Bs, you can improve the convergence. This means that you can reduce number of terms needed for evaluation. But I would say you can, for now, you can stick with those standard model parameters. Now what we do, we define strikes. So here is the our, let's say, running summation. So remember, we have a number of expansion terms from 0 until n-1. So this is this iteration. We do some change of variables. So we just redefine u, which is k times pi over b minus a. And then here we calculate the coefficients. So I already mentioned before, those coefficients are just hard-coded. So you can see, depending whether we have a call or put option, we need to define heap psi functions, which are just hard-coded here. So this is also given in the slides. Normally, you just implement once and you just reuse them. And you can see, like I already mentioned, you can do it for multiple strikes, multiple iteration terms. So it's not really strike, don't mix with K, capital K, but this is a number of term that is used in the summation. Okay, so those are the coefficients that we get, HKs. And then we perform this matrix. So first we define a matrix. This is the matrix corresponding to number of strikes versus number of expansion terms. And then we just, like I already repeated before, we calculate the product of the two. We make sure that first element of the sum is always half, and then the final line of the calculation. So we have a discounted strike times this product, the dot product. So it's actually in matrix, it's just a matrix multiplication of the characteristic function times the coefficients that we have calculated. And that basically it's it. So if we run this function, let's see. So what we see already. So let me just stop it again. Okay, because I have some breaking points. So we see here the following. So let's go here. It took us about 12 milliseconds to perform the price. So this is actually 1,000 of 12,000 or 10,000 of a second to perform the pricing. We have multiple strikes, and then we compare error. You see that basically this is the error that we see for each individual strike. Now, what we can also do, we can change number of expansion terms. So here's 32. We can do two times. So it's a 10 to minus 1. You see 64, we have 2. Let's make it 4 times 32. So you see we are already at 10 to minus 7. And here we can nicely see the comparison between cost method and Black-Scholes. You see it is not really a smooth line, and this is because we only use 3 strikes. Let me see if we can just also easily introduce additional strike. You can see by introduction of additional strike, this becomes smoother. Let's make it also 90 here. And then more strikes we will add. This function, the value will be smoother and smoother. And this also indicates that if you have to calibrate your model to multiple strikes, you basically, you will just change this line, and that will be enough. Okay, I think that should be enough. This function will be also available in the materials for this lecture.